Myself, Dr. Naresh Kumar, Associate Professor, Department of Mathematics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I want to discuss a linear differential equation of nth order with constant coefficient. So in this differential equation, which formula be applied to solve a linear differential equation of nth order with constant coefficient? So we are discussing several cases different on the value of q y is equal to cf plus pi. This is the main method used in a linear differential equation of nth order with constant coefficient. We apply the method that is very most important method, y is equal to cf plus pi. Cf means complementary function and pi is particular integral. If in our question the value of q is 0 given, then we find only one part of the solution, that is only complementary function. Then complete solution of the question is y is equal to cf only. We are not finding pi, particular integral, when q is 0 in our question. So now, first of all, we discuss a linear differential equation with constant coefficient. So here we are given equation 1. That equation is known as a linear differential equation of second order with constant coefficient. So in last video, I have also discussed about this differential equation. So this is the basic differential equation of linear differential equation of second order with constant coefficient. In this equation, P1 and P2 are number. P1 and P2 are constant. But here in right hand side, Q is the function of x only. Here say Q is equal to fx. Here we will discuss in detail how we can find the solution of linear differential equation of second order with constant coefficient. So this is the main general equation of linear differential equation with constant coefficient. So here highest order of this differential equation is 2 and P1 is number, P2 is also number, which are in multiply with differential coefficient, and in right hand side is Q. Q is the function of x here. So this is general linear differential equation of second order with constant coefficient. Now solution of 1. How we can find solution of 1? So we use here method. Which method we apply in equation 1? So that is very famous method in equation 1. Y is equal to cf plus pi. Cf means complementary function and plus pi is particular integral. So y is equal to complementary function plus particular integral. Y is equal to apply here complementary function and plus particular integral. There are two parts of the solution. First part is complementary function. Second part is particular integral. In our question, if q is given, then we find pi. If q is 0, then pi is 0. Pi is always 0. Particular integral 0. Here we will discuss in detail second part of the solution. How we can find second part. Main focus in this video, our main focus in this lecture, how we can find second part of the solution. Second part is particular integral. So how we can find in a differential equation particular integral? To find particular integral of 1, then q never 0. Q is not 0. Q never 0. Q is not must equal to 0. q is some function of x here. Q is some function of x here. Q equal to say fx. So here we start to find the particular integral. How we can find particular integral? So this is the general equation of 1 in our question. Our question is same as this type of equation 1. Our question is given. So formula for using particular integral, pi is equal to 1 upon fd into q. This is equation 2. Our question is in fd into by is equal to q. This is the type of equation. Fd some function of d. Fd means fd some function of d. Some function of d. Function of d. Fd is some function of d. Function of d. Fd. We will discuss here several cases depend on given function q in right hand side of the question, and also we will solve problem based on case 3. Case 1 and case 2 we have discussed in last two lectures, but in this case main focus case 3, if q equal to x to the power n, if in our question the value of x to the power n, q is x to the power n means x, x square, x cube and so on, x to the power n. If q is this function, then how we can find particular integral where n is positive integer, n is a positive integer. X to q equal to x to the power n is in some algebraic function. This is known as a algebraic function. So here we want to discuss how we can find the particular integral when q is x to the power n. N is positive integer means q equal to x, x square, x cube and x to the power n. So how we can find the particular integral of given differential equation, a linear differential equation of second order with constant coefficient. So now here apply formula for pi. Which formula we apply for particular integral in our question? So we apply formula is this 1 upon fd into q. Formula is 1 upon fd into q. This is the formula of pi. So pi is equal to 1 upon fd. Q is given here. Q is x to the power n. In this method, apply condition 4. So what condition apply here? I am writing the condition in our question. Condition is now here lowest power of d in denominator of pi taking common. Lowest power of d in pi. If we find out the particular integral, then we find out the lowest power of d in denominator of pi taking common and making binomial. So basically this point is very important, okay, to find the pi particular integral. So now we want to discuss here one problem based on case 3. If q is x to the power n, x to the power n means q may be x, q may be x square, q may be x cube and did this. So now problem 1 is d2y over dx2 plus 4 dy over dx plus 8y equal to x square. This is the question given in question paper. So now this question can also be written as or athwa. Or means d square plus 4d plus 8y equal to x square. How we can write this question? Here d2y over dx2. This is d square y. And dy over dx. This is dy. So after writing here d2y means d square y. And plus 4dy means 4dy. And plus 8y equal to x square. Now y is taken common here. y is taken common. So d square plus 4d and plus 8 into y is equal to x square. So this question convert in this form. D means is the d over dx, differentiating with respect to x. And d square means 2 times differential d2 over dx2 with respect to x. This is the second derivative, this is the first derivative of function. So equation 1, this is the question in our question paper, and equation 1 can be written as a 2. This is d square plus 4d plus 8y equal to x square. First, now, equation 2, solution of equation 2 is in two parts. First part is complementary function, second part is particular integral. So here we find first complementary function. First to find complementary function here, putting q equal to 0. Must putting q equal to 0. When we find out the complementary function, then q must be 0. This is the condition. So here q is x square. Q equal to is x square, and x square putting equal to 0. So we are taking here q 0. Then from equation 2 is this. Equation 2 becomes this. D square plus 4d plus 8y equal to 0. I am making this x square. X square is 0 here putting. Here in two equation function is given. Function is x square. But now we have taken function is 0. Then we get equation 3. So now putting d equal to m. D equal to m. I have discussed in last videos how we can put d equal to m. So d equal to m putting and removing y from equation 3. Y is removing. Y is the function. Function is not 0. So y is the removing from our question, and d equal to putting m. Then we get an auxiliary form of 3. We get an auxiliary equation of 3. So what is auxiliary equation? We get m square plus 4m plus 8 equal to 0. This is the equation 4. This is an auxiliary equation of equation 1. This is auxiliary equation of equation 1. In one equation, first of all, we are taking q0, and next we are putting d equal to m and removing y from the equation. Then we get an auxiliary form. Now factorizing of equation 4 here. This 4 equation factorizing. How we can factorizing this? So now we see that the equation 4 is a quadratic form. Equation 4 is a quadratic form. What is quadratic form? Ax square plus bx plus c equal to 0. This is quadratic form. Here x to the power degree 2, x to the power 1 and c. C is constant here. And a, b, c are constant. So this is a quadratic equation. So quadratic equation I have given ax square plus bx plus c equal to 0. This is 5 quadratic form. Here equation 4 and 5 both are same pattern. Equation 4 and equation 5 both have same pattern. 4 is also quadratic form in m and 5 is quadratic form in x. So now comparing equation 4 and equation 5, then we get the value of constants. From we find out the factorize of equation 4. So equation 4 is quadratic form. General quadratic form is given equation 5. So equation 4 and 5 comparing here. After comparing equation 4 and equation 5, then we get the value of constant A is 1 and V is 4, C is 8. Always if we are solving any equation which is quadratic form, then first we find out the value of A, B, C. A, B, C are multipliers of x square and x and constant. So A, B, C are 3 constants. We find first out the value of A, B, C here. Then solving the equation 4, any quadratic equation, we find out the solution with the help of Sri Dharacharya formula. Dharacharya have given a formula that is very important formula for solving quadratic equation, 2-degree equation of any variable. So basically solving equation 4, I am putting Sridharacharya formula. So I am writing here one formula, that is this. This is Sridharacharya formula. Dharacharya formula have proved this formula. This formula is ax square plus bx plus c equal to 0. Then he find out this formula. X equal to here minus b plus minus under root v square minus 4ac upon 2a. This is known as a Sridharacharya formula. Here two solutions are there, plus and minus. So here one solution is x equal to minus b plus under root b square minus 4ac upon 2a. And next solution is x equal to minus b minus under root b square minus 4ac upon 2a. So putting the value of a is 1, b is 4 and c is 8 here in this formula. Putting the value of constants which are getting from equation 4, which are given in m. Then after solving, we find value of m here. So m equal to 4, b is 4, minus 4 plus minus under root b square. 4 square minus 4ac. 4ac, 4 into 1 into 8 upon 2a, 2 into 1. So now here m equal to minus 4 plus minus under root 4 ka square 16 minus 4 is the 32 upon 2a 2. Now m equal to minus 4 plus minus under root minus 32 minus 16. 16 minus 32 means minus 16 here. So under root 16 is 4. So now minus 4 plus minus here under root minus 16 upon 2. M equal to minus 4 plus minus under root minus 16. Minus 16 I am writing here root minus 1 and root 16 into root minus 1 into root 16. So root minus 1 is I. I is imaginary number. I is an imaginary number. Imaginary number here. So I is known as a iota. I is iota. So here is root minus 1 is I and I square is minus 1. So I am putting here 4i. Root 16 is 4. So this is 4i and upon 2. Dividing by 2 this, we get minus 2 plus minus 2i. So this is imaginary roots. Imaginary roots are m equal to alpha plus minus I beta. This condition is given when b square minus 4ac less than 0. Then this condition comes here, b square minus 4ac less than 0. So we have got here imaginary roots alpha plus minus I beta, m is equal to. Here alpha is minus 2 and beta is 2. Alpha is minus 2 and beta is 2 here. So now using formula for CF, if roots are imaginary, which formula we are using here if roots are imaginary? So imaginary CF, this is the basic formula, general formula to find CF if roots are imaginary. So CF is equal to, I have given this formula, e to the power alpha x, c1 cos beta x plus c2 sin beta x. In last lecture, we have discussed this formula in detail, how we can find this formula. So here we are applying only formula to find complementary function if roots are imaginary. So CF equal to e to the power alpha x in bracket c1 cos beta x plus c2 sin beta x. This equation 6. Now putting value of alpha and beta in equation 6, then we get CF is equal to e to the power minus 2x, c1 cos 2x plus c2 sin 2x. This is 7. This is the complete complementary function of given equation 1. So equation 7 here, complete complementary function CF of 1. Half part is complete solved. Complementary function is find out. But now finding Pi of 1, apply case 3 and condition 4. So what condition here? Particular integral is equal to 1 upon fd into q. Pi is equal to 1 upon fd. What is fd here? Fd here, d square plus 4d and plus 8. This is fd. Fd is given in our question. So 1 upon fd, I am putting here fd into x square q. So now condition 4. What is condition 4? Here we are applying condition 4. Condition 4 is this: lowest power of d taking common in denominator of pi. Denominator of pi is this, denominator is this. Denominator is d square plus 4d plus 8 in pi. Denominator is fd. In particular integral, we see that denominator is fd here. So what is value of fd? Fd is d square plus 4d plus 8 here. So here I am giving some condition: lowest power of d taking common in denominator of pi and making binomial in equation 5. This is 5 equation. Then we get here pi equal to, now here I am taking this minimum power is 8. 8 number is minimum power of d here. Here is d to the power 2, here d to the power 1, here d to the power 0. So minimum power is taking common. So here we are taking 8 common. Now 1 by 8 is common, and 1 upon 1 plus d square plus 4d upon 8 x square. Now this is denominator taking in numerator. Denominator writing in numerator. Any denominator writing in numerator, then we get inverse. So whole to the power is minus 1, I am writing here, minus 1. Suppose here 1 upon 1 plus x, this equal to 1 plus x to the power minus 1. This is the denominator. We are writing in numerator this, then we get this result, 1 plus x to the power minus 1. So here this is equation 9. Equation 9 opened by binomial theorem. This equation opened by binomial theorem. So which formula of binomial theorem we apply here? 1 plus d to the power minus 1. This is function here. So here minus 1. Here is plus 1. So alternative sign is there. Here is 1 minus d plus d square minus d cube and so on. Here d is missing here. In this formula d is missing. 1 minus d plus d square minus d cube plus d4, alternative sign is there, and power of d is increased there. First term is 1, other the power is increase of d, and alternative sign is there in this. So here is fx here. Now pi equal to 1 upon 8. Same formula I am applying here, equation 9. Same formula. So this is d. Total this d here. 1 plus d to the power minus 1. So I am writing here 1 minus d plus d square is whole square plus d cube, and this whole cube and plus this up to infinite. This series goes to up to infinity. And this is function of x is x square. So here 1 upon 8, next term 1 upon 8, 1 minus. Here d square plus 4d by 8. Now open whole square here. So d square ka whole square d4, 4d ka square is 16d square, and multiply of twice here. So 4 to the 8d cube here upon 64. Next here is d cube. Maximum in last term is maximum power is d6 and minimum power d cube. Total power this to this. So we cannot write this term here. So here next term is 1 upon 8. So multiply by here x square. X square taking inside the bracket. This function taking here inside. So here I am writing here x square 1 x square and d square x square 4d x square by 8 plus d4 x square and 16d square x square 8d cube x square. Other term are vanished. I am not writing other term. So here is 64. Now we know that here what is d of x square. So here I am writing here d of x square is 2x. One time differential of x square, d of x square. d square of x square means this is 2. 2 times differential of x square, that is 2. d cube of x square, d cube of x square is 0. And d4 of x square means this also 0. So all higher order derivative of d more than square, that is all 0. d cube 0, d4 0, d5 0. So I am not taking here cube, this term and other term are all 0. So these value from equation 11 putting in 10. From equation 11 putting all values in equation 10, then we get here. So x square, here is 2, here is 2x and here is 2. Where is d square? There is 2, there is d, where is 2x. So pi is equal to here 1 upon 8 x square minus 2 plus 4 to 8x upon 8 plus 32 upon 64. So here I am taking here this 32, 1 ja 32, 2 ja 64. So here is 1 upon 2. Here is 2 by 8 minus 8x by 8. So I am taking here LCM. LCM is 8. Now 8x square minus here is 2 plus 2 minus 8x. 2 minus 8x or here is plus 2 4 ja 8. So here is 4. Here is 1. So 2 4 ja 8. Here is 4. So now this 8 8 ja 30. 8 8 ja 64. 8 8. I am writing here 1 upon 64 and in bracket 8x square minus 8x and plus 2. Now 2 is common. I am taking 2 is common here, 4x square and minus 4x and plus 1. Now upon 64. So 2 here 32. So final answer 1 upon 32 and in bracket 4x square minus 4x and plus 1. So this is answer pi. So I am getting this pi. This is complete particular integral of 1. Now equation 13. Equation 13 is complete particular integral of 1. Now complete solution of 1. Here we want to write the complete solution. Our solution in two parts. First part is CF, complementary function. Other part is particular integral. So here we are adding complementary function and particular integral. Both solutions we are adding here. Then we find the value of y. So now complete solution of equation 1 is y is equal to CF plus pi. CF is complementary function, that is first part of the solution, and particular integral, that is second part of the solution of linear differential equation with constant coefficient. So here we are adding both solution. Y is equal to CF plus pi. So now adding equation 7. In 7 we find out the complementary function. And in equation 13 we find out the complete pi. Then adding both equation, then we get here y is equal to e to the power minus 2x c1 cos 2x plus c2 sin 2x and plus 4x square minus 4x plus 1 upon 32. So this is the complete solution of equation 1, question 1, problem 1. In this solution, this part is complementary function and this part is particular integral. So in complementary function, arbitrary constants are there. So second order differential equation, so here we find out two arbitrary constant. If third order differential equation, then we find out three arbitrary constants. So this is the complete solution. Next, I want to discuss same problem, same type of problem, problem 2 based on case 3, if q is x to the power n. Again solving same problem. Problem is different, but method is same. If q is x to the power n, q is an algebraic function, then how we can find complete particular integral? So I am solving here next problem. d2y over dx2, second order of the function, second derivative here, plus 10 is number, dy over dx, first derivative here, and plus 25, y is equal to x square. So here this equation also can written in this form. D square plus 10d plus 25 y equal to x square. Now solution. d2y over dx2 plus 10 dy over dx plus 25 25y equal to x square. This is given equation 1 in our question paper. This question is written in our question paper. Either this second type also given in our question paper. Any type of 1 or type of 2. Any type of question given in our question paper, but we apply same method here. Y is equal to CF and PI. This is second form is written in derivative form, D form. D means derivative. I am already telling D is D over dx. And here D square is D2 over dx2. This is the second order derivative. So D2 over dx2 we write D square. So y taking common, and D2 over dx2 I am writing D square, and D over dx I am writing D, and y is common. So equation 1 convert in equation 2. So this is second equation here. Now first part of solution is particular integral. First we find out complementary function. Here is not particular integral. Here is complementary function. First part of solution is complementary function. Complementary function. Complementary function. First part of solution is complementary function. So first we find out complementary function, then putting q equal to x square. Q must be 0. When we find out CF, then Q must be 0. But here Q is a x square. So I am putting x square equal to 0. So our equation 2 becomes in equation 3. D square plus 10D plus 25y equal to 0. Here is x square in our question. But I am taking here 0 in place of x square. So this equation convert in 3. Now putting D equal to m here. D equal to small m. And removing y from equation 3. In equation 3, putting d equal to m and y is a function, and y removing from the question. Then we get an auxiliary form of 1. Auxiliary form of 1. So m square plus 10m plus 25 equal to 0. This is equation 4. This is 3. Form of equation 3. Factorizing of equation 4. Then we get. So now we see that this equation 4 is a perfect square. What is perfect square? This is m square plus 10m, m plus 25 equal to 0. If our equation is a square plus 2ab and plus b square, then this is perfect square. This is a plus b ka whole square. Same, this is our question, m plus 5 ka whole square. M plus 5 ka whole square. So our factorizing equation 4, then we get m plus 5 ka whole square equal to 0. This is equation 5. Now m plus 5 ka whole square equal to 0. Whole square, x square is means x into x. We can write this x into x. So I am writing here m plus 5 into m plus 5 equal to 0. If m plus 5 equal to 0, then m equal to minus 5. This is the value of m1. m1 means first root of m. And if m plus 5 equal to 0, then again m equal to minus 5, that is m2. Now m equal to minus 5, roots of m are equal. Then formula for CF, if roots are equal, if an auxiliary form has equal roots, then which formula be applied in our question? So here I am writing this formula equation number 6. This is the formula for CF when roots are equal. When an auxiliary form have equal roots, then formula is this, apply in the question. Y equal to C1 plus C2x e to the power mx. M is minus 5 here. So y is equal to C1 plus C2x into e to the power minus 5x. Y is equal to C1 plus C2 x in bracket e to the power minus 5x. This is CF, complementary function. Here C1, C2 are arbitrary constant. In our complementary function, if our differential equation is 2 order, then we find two arbitrary constant. So C1 and C2 are two arbitrary constant here. This formula applied when roots are equal. Now, Equation 7 is complete CF of 1. Now finding second part of solution. Now finding second part of solution is PI. PI means particular integral. How we apply the, here we apply the formula of PI, formula of particular integral. So particular integral 1 upon FD into Q. This is basic formula. Basic formula to find PI. Particular integral. Basic formula. This is basic formula to find PI. 1 upon FD into Q. PI equal to, but FD, what is FD in our question? FD is, here FD is D square plus 10D and plus 25. This is FD. So now 1 upon FD, putting value of FD here, D square plus 10D plus 25. This is Q. Q is X square here. Q is the function of X here. Q is the some algebraic function here. So X square is an algebraic function here. Apply case 3. Again apply case 3 and condition 4. D over dx represented by capital D here. Here Q is X square, an algebraic function. Then to find PI. Taking lowest power of D common in denominator of PI. Particular integral have numerator and denominator. So in denominator of PI, taking lowest power of D is common. In equation 8, making binomial. So equation now we have from equation 8 this result 1 upon D plus 5 ka square into X square. FD, this is perfect square. D square plus 10D and plus 25. This is D plus 5 ka whole square. This is perfect square. So I am writing here D plus 5 ka whole square in next equation 9. D plus 5 ka whole square. But this is the condition I am using here. Taking lowest power of D is common. So here is D to the power 0. In this function D to the power 1. In this function, in this number D to the power 0. So lowest power is D to the power 0 here. So 5 is taking common here. If we are taking here 5 common means 5 ka square common. Square is common. So here y equal to 5 ka square means 25. I am taking 1 upon 25. And 1 plus. If we taking here 5 common, then here is 1. And D, here is D by 5. This 5 goes upon denominator of D. D upon 5. 1 plus D upon 5 ka whole square. So I am writing here 1 plus D upon 5 ka whole square. Whole to the power minus 1 I am writing in numerator. 1 upon here D plus 5 ka square. Okay, X square. So I am writing here 1 to 25. 1 upon. Here 5 is common goes. So square is also goes. 5 ka square 25. So I am writing here 1 plus D by 5 ka whole square. This term writing in numerator. So 1 upon 25 and this 1 plus D by 5 ka whole to the power minus 2. So I am writing here whole to the power minus 2. Apply here binomial. This formula applied here 1 plus D ki power minus 2. Here this is 1 plus D, this total D to the power minus 2 here. 1 plus D to the power minus 2 fx equal to, alternating sign is there. We apply here formula 1 plus x to the power minus n. Minus n. This formula apply here. 1 minus nx plus n into n minus 1 upon 2 into x square plus n into n minus 1 n minus 2 upon factorial 3 into x cube. This is binomial formula I am using. So n is here minus 2. N is total n is minus 2 here 1 plus n. So here plus this plus. So now putting 1 minus here minus 2d plus 3d square minus 4d cube. We are opening this, then we get this result. So now here 1 upon 25, 1 minus n is 5 and d upon 5 n x and n minus 1 upon factorial 2 into d is x square, and n minus 1 n minus 2 upon factorial 3 x cube, and plus this goes up to infinite series. If in binomial the power is negative, then series open up to infinity. So y equal to 1 upon 25, first term is 1 minus, here 5 is cancel, so here is only d, here is d, 5 is cancel, here is d, plus here 6 5 is 30 and divide by 2, here is 15, d square upon 25, and here is, this is factorial 3 is 6, so this cancel, so here is minus sign, and this 7 5 is 35 and 5 ka cube 125 d cube, and plus this into x square is function is out of the bracket. When we write this function inside, then that is differentiate, because d is differentiation here, second order, third order and first order differentiation here. When we multiply by this x square in bracket, then this function differentiate in each term. So after multiplying this term here, 1 minus d, 3d square by 5, 7d cube by 25 into x square. So now taking x square inside the bracket, then we get 1 upon 25 x square dx square 3d square x square by 5 minus 7d cube upon 25 x square, and plus this. We know the derivative of x square is given as follows, dx square is 2x. If dx square is 2x, differentiating with respect to x one time, so x square, differential of x square is 2x. 2 times differential of x square is 2. 3 times differential of x square is 0. 4 times differential of x square is 0. So other higher order derivative is all 0. So these values putting in 13, from 14 equation putting in 13. So here is x square 2x and this other is all 0. So now this term is total 0. X square minus 2x, 3 2, y 5, 3 2 is 6. So 5 is taking LCM here. This equal to 1 upon 25. 5 is taking LCM here. So here is 5x square and minus 10x and plus 3 2 is 6 here, 6. So here 25 5 is 125. 5x square minus 10x plus 6. This is equation 15. So equation 15 is complete particular integral of equation 1. Now complete solution of 1 is y is equal to CF plus PI. This is basic formula to find the complete solution of ordinary differential equation with constant coefficient. So now adding equation 7 and equation 15, then we get here complete solution. Y is equal to C1 plus C2x e to the power minus 5x. This is complementary function of the given equation, and this is the particular integral of the question. So total, after adding complementary function and particular integral, we get the complete solution of the given question, which is the linear differential equation of second order with constant coefficient. But in our question, q is x square. Q is an algebraic function. X square, maybe x square, x cube, any type of q is given in this case. Then we can solve same method. We apply same procedure in our question. First we find complementary function. Second we find particular integral. And then we adding both solution. Y equal to CF plus PI. So this is the required complete solution of equation 1. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.